Good morning or good afternoon, depending on your time zone. I'm here to talk about some work I did with a number of students at University of California, San Diego. I've now moved to University of Southern California, just up the road a little bit. So let me give some background first. There's been some amazing progress in the past 10 years or so on image classification using convolution neural nets. They do things like can distinguish dogs from cats, and they're being applied more and more in medical domains. So I've been working on a number of medical domains, including diagnosis of glaucoma from images of the retina, or diagnosis of skin cancer from images of molds, etc. Although there's been a lot of progress in image classification, convolution neural nets remain a black box, and there's been a lot of work on explaining the image classification. The way this typically works is you identify a region of interest. So in the image here, there are several highlighted areas, and those areas correspond to the areas that the neural net thinks is important. However, there's not been a lot of work on, is there agreement between what the expert identifies an important region and what explainable AI finds as an important region? And what little work there has been shows there's room for improvement. And in this paper, we talk about one way of finding that improvement, which is by using ensembles of neural networks, not just a single network, but several different neural networks to do classification, and then combining the explanations. So as more background, for convolution neural networks, you can present them with images such as images of birds. Here's pictures of grebes and golden eyes, and they learn to classify and distinguish these species. And then for explainable AI, the goal is to highlight certain areas. So here's some of the first examples of explainable AI, explaining why there's a dog in an image and explaining why there's a cat in the image. And in each case, they highlight a certain area of the image using a heat map, and that explains why this is a dog on the left or why there's a cat on the right. There's been many different approaches to explainable AI, and you can divide them into bottom-up and top-down approaches. So the bottom-up approaches manipulate an image and see how that changes the classification of the image. So either by obscuring it or changing certain parts, things like line or image shape are examples of these bottom-up. Top-down ones, there's actually two different types here. Gradients look at the hidden units and the activations on those hidden units to identify important features. And then modified backprop actually propagates relevance from the output all the way back into the input image. On the next slide, we see several different types of explainable AI, and there's been probably 10, 15 different types that people are exploring. And all of these, in this case, are looking at bird classification. So I will actually flip back and forth between bird classification and medical image processing throughout this talk. Then the question is, how well does the explainable AI identify regions of interest? So what we have on the left here is actually a photograph of the inside of the eye, showing the optic nerve and other areas. And we can look at that, an ophthalmologist can look at that and determine whether one has glaucoma or not. When we run various convolution neural network algorithms on them, we can get up to 95% accuracy. When the ophthalmologists do this, one of the things they look for is thinning of the rim of the optic nerve. And that shows that you're losing some nerves, and that's why you lose some vision with glaucoma. And they can identify the location of that. And they actually do this by the clock angles. So, you have damage at 11 o'clock. When they recorded the images and the damage, it turns out that we're extremely accurate at getting the classification right. We're just a little bit better than chance at identifying the same regions that the experts identify. So that led us to want to start to do research on how we can improve what area of the image the neural network is focusing on. And by the way, it's not just my own work. Others have noticed this as well. So in pneumonia detection, people look at what area of the lung has pneumonia. And again, they're finding that most of the explainable AI algorithms, although the CNN does a good job at classification, doesn't really do a fantastic job at localizing where the pneumonia is in the lung. And getting to another example in the bird species identification, looking at this particular image of the bird, one neural network concentrates on the face, a different neural network, just run with different random weights, will concentrate on a different area, in this case, the wing. And the reason for this is the neural network isn't trying to find every important region, it's just trying to find one sufficient means of distinguishing the examples. But this leads us to think we might be able to combine those two images to find several important regions. And in fact, maybe that gets to the question of what's the role of the explanation. One role of explanations is developer-centric, so you can explain how the neural network works and get confidence in that. But what we've been looking at, we're calling expert-informed explanations. We're trying to explain the same way an expert does, and even user-centric, trying to create explanations that users like. So below, we see an image from a birding guide that shows how you can identify these two different but quite similar species of birds. And you can see that it's focusing in on this spot on the face and focusing in on the wing. So one of the things we've been looking at is, instead of just using a heat map, can you find the center of mass of the heat map and then have an arrow point to that center of mass? So in doing this bird classification, instead of just popping up red and green on the image, we can pop up arrows with labels like large bill and wing bar, which explains why that area is, why that bird has a certain classification. And the formula for the center of mass is below, but it's derived from the physics idea of the center of mass. So if we see a lot of variability in explanations, maybe if we combine them, this is really the same as the bias variance trade-off in accuracy, but now we're looking at the accuracy of an explanation. So on the top, you have 4 different networks identified why this bird has a striped wing. And they have slightly different explanations. Some bleed into the face, some go outside the bird body. But if you take the average of those, you focus in much better. This is even more apparent when you look at the heat map, when you look at the center of mass of the heat map. So the red arrow points to the average center of mass, and the other arrows point to one particular network focused on an area near the wing, but not getting it quite right, where the average does better than many of the others. Similarly, when looking at the bill, the average does better than a number of others, including those that are pointing more at the body of the bird. So then what we decided to do is average multiple explanations. And the way you can achieve this is you create n different neural networks, each with different initial conditions. So when you train a neural network, it has random weights. And with different random weights, you learn something slightly different. They tend to have very similar accuracies, but unfortunately, they have slightly different explanations, more varied than the accuracy. But we can take advantage of that by averaging over them. Another technique from the 90s for doing multiple networks is bagging by Leo Breiman, or bootstrap aggregation, where essentially you resample the training data with replacement. So you create n new training sets. Some of them are missing some examples and having extra emphasis on other examples because you've resampled with replacement, but then you can form different neural networks with each of those and then average them. Another technique, and this is from the 80s, is you create n buckets of your training data and you leave one of those buckets out. So this isn't doing the replacement. This is just using, say, 90% of the data, each learning a different neural network, and then you can combine them. So what we're going to show is you can use this for any explainable AI algorithm, and also really for any neural network algorithm for doing classification. And then you can combine the heat maps. And right now we're just doing a simple average, although if you look at accuracy, people have found ways of weighting the heat map, weighting the neural networks differently. Here right now, we're just starting out simply averaging them and seeing what effect that has. So I'm going to describe experiments on a number of different data sets. We're using two data sets here. One we call high-res birds, which has about 14,000 images of birds divided into 66 different species. And for each of those images, we know the bill length of the bird, whether it's short, average, long, or very long, or the pattern on the wing, whether it's solid, spotted, striped, etc. And then we also know the location of some parts of the wing, like the bill, or some parts of the bird, like the bill or the wing. And then another data set we use is a melanoma data set with about 2,500 images, and about half of those have melanoma and half are healthy. And then they have attributes that describe the image, like is the border irregular or are there white streaks? And for each attribute, we actually have a mask that says where it is. So this mask indicates where on the image the border is variable in color. And so what we'd like to do is see how well our explainable AI algorithms can replicate the regions here or identify the wing or the bill when figuring out whether it has a long wing or a spotted bill. And then the experiments, we're going to compare two different things. One is the ensemble average. That's where we use our technique of averaging over n heat maps. And then we're going to compare that to an individual run where you just do a single run and see if the average increases the accuracy. And then we have two different metrics. One is the center of mass distance, where we look at a key point where someone has indicated the bill is here with a point or the wing is here. Or we look at the regions and see how they overlap. And the method we use there is intersection over union. So the intersection identifies what areas are in common between the ground truth and the predicted explanation. And the union indicates what's in one image or not the other. So a large intersection means you're identifying it correctly. If the union's too large, it means you're including irrelevant areas. And then we ran a number of different experiments with this technique. So for instance, trying to determine the bill size individually, we get this as the average distance, but the ensemble improves upon 5 different explainable AI algorithms. And our improvements are generally in about the 10% category. So, and you see this with increasing accuracy of using ensembles as well. It tends to reduce error by about 10%, or in this case, increase the accuracy of the explanation by about that much. Then when we look at identifying the wing patterns, we see the same thing. And this is using the VGG neural network architecture. We've also tried doing this with ResNet, a different architecture. And again, in this case, the ensemble has a better accuracy of the explanation than just using one individual neural network. And then for melanoma classification, this is using intersection over union, where higher is better. And in this case, the ensemble, again, has a better result on this metric for 4 different explainable AI algorithms than looking at individual networks. And one of the things we did is we wanted to look at the contribution of the intersection, that is there more overlap with the ground truth, or and the contribution on the union as well. And in general, this technique improves the intersection. So there's much more overlap with the ground truth. And it somewhat decreases the union, but in one case actually increases it. So the major effect is identifying more of the relevant areas, which makes sense in a way because each neural network will find one sufficient way, and this will combine in several sufficient ways of doing the classification. And then we also looked at, mentioned different approaches to generating multiple models. The approach we use most often is different random weights, but using k-folds classification or bagging, we also improve upon from the individual model. Another experiment we ran was to look at the size of the ensemble. So starting with 2 different networks and then increasing it up to 32. And what we often find in this is diminishing returns. After a while, somewhere between 8 and 10 units, you get diminishing returns. And this uses 2 different algorithms. We're doing this with GradCam and Lime. And again, in each case, you do find this leveling off at the end. And then finally, I want to discuss an experiment we did with human bird watchers. If averaging increases the number of relevant regions and decreases the irrelevant regions, will expert bird watchers be able to figure this out? So we constructed a number of examples of birds that are highlighted. And again, on the left here are the individual, a single neural network. And on the right are the average, in this case, of 11 different neural networks. And you can see it picks up extra features like the color of the bill or this spot on the face compared to the individual network. So then we showed the images to birders, but they didn't know which was done by average and which was done by an individual network, of course. And we asked them 2 questions. One was, does the highlighting emphasize areas of the bird that are important? And the other was just simply, would they recommend using this highlighting? And the next slide shows the results. So there were 28 participants. Each was shown 48 different birds that were highlighted. And we're doing a within subject comparison. And then using a single neural network, they thought it found on a scale of 1 to 7, they thought it found the important area on average 4. But if you average it, that increased to 5.5. And then similarly, would you recommend this increased from 3 to 5? And all of those are significant using a standard test used in psychology. So let me wrap up and see if there's time for questions. But so basically what we've done is we've shown that regions of interest identified by the explainable AI algorithms should correspond to the regions that are important. And averaging over multiple models seems to improve this correspondence for any neural network algorithm and any explainable AI algorithm. And then we showed that experts can detect the difference in explanations and prefer those by averaging. And then in future work, we're looking for better ways of combining multiple models. And we're also looking at eye tracking data, where instead of having the expert annotate the image, we just look at what they're looking at and use that as a means of identifying the important regions of the area. So with that, I'm happy to take any questions.